after the mission, or in case of emergency, on the Earth departure stage of the mission. The launch sequence is as follows. The Agor module is the first one to be launched into the low Earth orbit. It waits there for the first fuel tanker to arrive. The Agor module is launched atop Ariane rocket or the Proton M rocket. We have considered two options. Then the fuel tank is launched atop Proton M rocket. It docks to the Argo module and waits. The second one is the heavy lift upper stage. It is launched atop the Proton M rocket. It docks to the living module and waits for the first fuel tanker to arrive. The tanker is launched on top the second Proton M launch vehicle, it docks to the heavy lift upper stage, has the fuel transferred to the upper stage, undocks, and the orbits and burns in the Earth's atmosphere. The second fuel tanker does the same thing, and after that, the upper stage is fully fueled. The 5 vehicle to be launched is the Soyuz spacecraft, on top the Soyuz 2 launch vehicle. It is launched, it docks to the living module, and the 6th launch is the launch of the hydrogen-oxygen upper stage, which is officially named KVTK after its Russian abbreviation, and it is launched atop Angara A5 vehicle. So it docks to the heavy lift upper stage, and everything is ready for Earth's departure. Next slide, please. Okay. The overall duration of an orbit assembly is about 5 months. Months after it is over, the KVTK gives the first burn and transfers the vehicle into elliptical transfer orbit. It undocks, and in the perigee of that orbit, the heavy lift upper stage burns, setting the vehicle on its way to the Venus. It takes the vehicle about 140 days to reach the Venus. We fly at a distance of 12,000 kilometers above the surface of the Venus, and the gravity sets us on our way to Mars. The Mars altitude, flyby altitude, is 300 kilometers, and after Mars, we are going back to Earth. The trajectory ends on approach to Earth. The Soyuz spacecraft separates from Argo living module, and it separates in 3 parts, and the descent module enters the atmosphere and performs a landing with 2 entries. Next slide, please. A few words about trajectory design. We chose for our project a free return Earth, Venus, Mars, Earth trajectory. This trajectory has only one propulsive maneuver, trans-Venus injection, after which the vehicle coasts all the way to Venus, then Mars, then Earth, performing only small trajectory corrections on its way. There are 3 critical parameters to such type of a trajectory to be implemented practically. They are the delta V requirements for the trans-Venus injection, the time of flight, and the entry velocity. HLUS, Edelman, and others discovered that there is favorable combinations for these parameters for trajectories in the end of 2021, and we decided to explore this possibility closely and conducted our own calculations. Next slide, please. We used an approximate computational model. You can see the assumptions we made to do it. After all, the problem of calculating a trajectory was transformed into solving a system of 6 nonlinear equations, which we programmed into MathCapster software and solved multiple times. We calculated different trajectories for different Mars flybys, flyby altitudes, and for different launch days. Next slide, please. We got some graphs which you can see here on the slide, and those graphs told us that for our mission it is better to fly at Mars at the least altitude possible. As you can see from the table, when HM, the Mars flyby altitude, decreases, the entry velocity and the time of flight increased too. The situation with the launch date was not so obvious. For the earlier dates, the delta V requirements and the entry decreased too, but the time of flight grows. But in the end, the delta V requirements proved to be the most critical parameter for the flight, and we were bound to choose the earliest date possible. Next slide, please. It was the date of the 17th of November, and as you can see from the table, with the limit of delta V capability of our departure vehicle stack, which is 4.2 kilometers per second, we have the launch window of a week, only 7 days. And the table shows that the delta V requirements are critical here, because if it weren't for them, we could have wider launch vehicles. For example, 35 days, if we had only constraints about the entry speed. We chose to have Mars flyby altitude at 300 kilometers for safety reasons. And you can see some parameters of our nominal trajectory. Next slide, please. The transvenous injection maneuver is split into parts. The first one is performed by the KVTK. It is shown in the red color in the picture, and its delta V is about 1 kilometer per second. The second maneuver is implemented by the heavy lift upper stage. Its delta V is about 3.18 kilometers per second, and the gravity losses for this scheme are estimated to be about 55 meters per second. Next slide, please. We did not do any calculations of our own regarding the descent of the descent vehicle in the Earth's atmosphere. Our project implies cooperation with Rocket Space Corporation Energia, and it includes negotiating a commercial contract on conducting any research necessary for proper Soyuz modernization. But we can say that most probably the trajectory will include two atmosphere entries. After the first entry, this descent capsule will exit the atmosphere on the suborbit trajectory, and then it will enter the atmosphere for the second time and perform the landing. The reason we hope that it will be possible in the near future is because there was a zone program under which such type of a descent trajectory was successfully implemented. There were two unmanned probes, Zone 7 and Zone 8, in 1969 and 1970. They performed a successful landing, though the entry speed was about 11 kilometers per second. But we hope if Energia could do it in the 70th, maybe today it could do it also. The next slide, please. The next few slides will be devoted to the transportation system elements design. We were trying to use existing technologies whenever it was possible, and almost of all the elements in our transportation system are based on existing vehicles or their modifications, except for the KVTK. I will tell you about it later. And you can see the mass budget on the slide, and the total mass of the departure vehicle stack is about 100 tons. Next slide, please. The heavy lift upper stage is based on the third stage of the Proton M rocket, but it has to be modified. Its service model is to have an active docking node, and it is to have its life increased, and it has to have refueling capability. Because the main engine of the third stage of the Proton M rocket can be ignited only once, we had to add an auxiliary equipment bay into our design. It is based on ATV. It has its own propulsion system, ATV based, and it is used to deliver the heavy lift upper stage from its initial launch orbit to the parking orbit, where it docks with the leading module. And the auxiliary equipment bay is jettisoned before the ignition of the heavy lift upper stage. Next slide, please. The fuel tank is based mainly on the ATV system, but it has to have small diameters to fit into Proton's fairing limits. The integrated cargo carrier has to be modified to contain tanks with fuel for the heavy lift upper stage, and its service module will be much smaller because we need only 500 kilograms for fuel for deliver the fuel tanker from its initial orbit to the parking orbit. And the fuel delivered to the upper stage is 15 tons for each of the tankers. The next slide, please. The KVTK upper stage. It is the only element that does not exist yet. It is currently under development at the Khrushchev State Research and Production Space Center in Russia, and its first launch is planned for 2021. And our project implies that we just buy this vehicle for our project. The next slide, please. The modified Soyuz spacecraft, not surprisingly, it is based on the design of the Soyuz MS spacecraft. Its major modification is for its descent capsule, which is to ensure the safe landing at speeds of entry speed, and its lifetime has to be increased up to 2 years in docked condition, and it has to be suited for the crew of 2 instead of 3 that we have now. The next slide, please. The Argo-Living module, it consists of 3 compartments, the transfer compartment, the crew compartment, and the service module. The crew compartment is based on the analogous compartments at Zarya and Zvezda modules of the International Space Station. It has an observation dome on it, similar to the ISS cupola, but it is smaller and it is lighter. And it has a high gain antenna on it. The crew compartment is basically the ATV pressurized compartment, but it is 1 meter longer to give the crew more space inside. The service module on the Pointer is shorter because we don't need all the fuel tanks of the ATV, so it is shorter and lighter, and it has its solar arrays increased. And you can see on the slide that the total dry mass of the Argo-Living module without life support system and crew supplies is 8 tons, 200 kilograms. The next slide, please. The life support system is mainly based on the currently used on the International Space Station. The only piece of equipment that is not used there now is the system that would allow to recover water from solid wastes. It does not exist yet, but there are some laboratory experiments conducted in Russia nowadays. But even if it is not ready by 2021, it is not a critical component of the mission. And some of the equipment should be modified for our mission. For example, the Electron device, which produces oxygen from water, on the International Space Station, it now throws the hydrogen left from the chemical reaction to space, and we want it to be transferred to the Sabatier reactor. And the same goes for the Vozdov device, which is to transfer the CO2 it absorbs to Savage reactor as well. Apart from recovery system equipment, we are planning to have a greenhouse on board. It is not intended for food replenishment purposes, but we believe that it will have positive psychological effect on the crew. The next slide, please. The interesting thing about the system that with the cycles closed, we actually can have the water amount on board increasing instead of decreasing due to inevitable losses. It happens because we have an incoming source of water. It's water from food. We estimated it to be about 1 kilogram per day for 2 persons. And the water, it goes through the crew and then through the recovery systems. And it covers the losses in the system, and we even have water excess. If we have the recovery system which extracts water from solid waste, we have the excess of plus 0.72 kilograms per day. And if we don't have that system, we have the excess of plus 0.42 kilograms per day. The life support system mass was estimated to be around 2.5 tons. We did not do any specific calculations about the thermal control. We just assumed that it will be based on the ATV systems. Next slide, please. We're planning to use the NASA Deep Space Network for communication in deep space and the tracking and data relay satellite system for near-Earth communications. We will have one high-gain antenna on board and two low-gain antennas and some other equipment. Please. Next one. Sorry, I can see. Yep, the one I need. The navigation system includes an inertial navigation system, some optical sensors, and we are planning to use the same equipment as for communication for radio navigation. And we use the NASA Deep Space Network here as well. The next one, please. For attitude control, we use 4 gyrodynes, with one being in reserve, and attitude control thrusters. Right now we have 28 thrusters on a GO module and 24 thrusters on Soyuz. The trajectory corrections are to be made either by 4 main engines on Argo module or by the main engine on Soyuz. We will also have the cruise docking navigation system for docking purposes. The next slide, please. We estimated the power needed for the mission to be about 6 kilowatts, and we calculated the area of the solar arrays, which is the main power source for our mission. And the area is about 41 square meters. For reserve power, we will have 2 nickel hydrogen batteries, one active and one in reserve. The next slide, please. Radiation protection. There are 3 possible sources of radiation for interplanetary flights. These are galactic cosmic rays, solar flares, and radiation belts. We're not going to spend a lot of time in the radiation belts for our mission, so we concentrated on analyzing galactic rays and solar flares radiations. Recent studies based on the results obtained from the radiation assessment detector on the Mars, the MCL spacecraft, show that there is an anti-correlation between the radiation from galactic cosmic rays and solar flares. It is connected to the solar activity. When the sun is active, we have more solar flares, but on the other hand, the stronger magnetic field of the sun deflects more galactic rays, so we have lower intensity for them. So, as strange as it may seem, it appears that it is more beneficial to have an interplanetary flight during the high solar activity. And it's just the case for our mission. According to Lee and others, the next solar cycle, the 25th cycle, is to begin in 2019, and its maximum will be reached in October of 2023. And so we will have high solar activity during the mission. We estimated the total dose equivalent for our flight. It is about 687 millisievert, which corresponds to about 1.1% of cancer risk later in life, with no special measures for radiation protection. And it is well within the NASA limitation of 3%, so we didn't include any special measures into our design for radiation protection for now. The next slide, please. The crew support system should include crew supplies like individual gear, hygiene stuff, spacesuits and other protection gear, and also medical equipment such as health monitoring equipment, preventive care equipment, and various medical kits. We assumed that all supplies, equipment, and procedures of the crew support system are analogous to those on the ISS. The next slide, please. Thanks. You can see the final mass budget for the flyby vehicle here, and we left some fuel reserve on Argo for doing corrections and attitude control, and we have 2.2 tons of mass reserve for crew supplies and equipment. We also have some fuel reserve on Soyuz, and together with the fuel on Argo, it gives us about 190 meters per second.
1 minute left.
Delta P for corrections and attitude control. The next slide. I'll probably skip that later and running out of time. The next slide, please. So here are the agencies involved for our missions. The main space operation launch center and
Okay. Это все?
Now, 3 more slides, please. Can I have the next one? With the mission schedule. Yeah, you can hear the mission schedule here. And we have the first phase when the vehicles which we are modifying have to be developed. 2 years, 2017 and 2018. And after we have the final design, we have to start manufacturing the vehicles and the launch vehicles and start selecting the crew and its training. The next slide, please. Here you can see the cost estimation.
You have to finish.
Yep, just a little. Okay, you can see from the table cost. And next slide, please. The last one. So in our project, we tried to make the maximum use of existing technologies, but we have 2 crucial developments. It's the modified Soyuz and the KVT stage. KVT stage is crucial because launch is planned for 2021. It's very close to our mission. And finally, I'd like, on behalf of my team, to thank Mars Society for such great contest. We've had a great time participating. Thanks. That's all.